Okay, in this example, we're going to look at another infinite series, and we're going to end up using the integral test also on this particular series. And so we have the series 1/2 plus 1/5 plus 1/10 plus 1 over 17 plus 1 over 26 plus blah blah blah. Now, if we look at perfect squares, 1 and then 4 and then 9 and then 16 and then 25, you notice that the denominators of this series are all 1 more. So 1 plus 1 is 2, 4 plus 5 is, 4 plus 5. 4 plus 1 is 5, 9 plus 1 is 10, 16 plus 1 is 17, 25 plus 1 is 26. And so the formula for this is going to be sum n equals 1 to infinity of n squared plus 1. Now, if we're going to use the integral test, the function that we're going to use to kind of match our sequence here needs to be positive, needs to be continuous on 1 to infinity, and it also needs to be decreasing, and then we can use the integral test here. And so our function is going to be the same thing. Instead of n, we'll have x squared, or n will have x. This is certainly positive. This is continuous on the real numbers, so those conditions are met. Now we just got to look at the derivative here. So there's low d high minus high d low all over low squared. So that's going to be minus 2x over x squared plus 1 quantity squared, and this is going to be negative as long as x is greater than 0, which is perfect for us because we want it to be, we want this first derivative to be negative on 1 to infinity, so that gives us the decreasing. So we have our conditions met to use the integral test. And so what we're going to look at is the improper integral from 1 to infinity of 1 over x squared plus 1 dx. Okay, so that's just a nice arctan. Because it's an improper integral, we'll go ahead and write what that means. So this is the limit as b goes to infinity, and we'll go ahead and integrate it. Arctan of x, and we're going to evaluate that from 1 to b, and we'll go ahead and evaluate it. So limit as b goes to infinity of the arctan of b minus the arctan of 1. Okay, and so maybe it's not obvious if we don't remember what the graph of arctan looks like. So we're going to go ahead and we're going to graph tangent first. We're going to graph tangent in its restricted domain, and then we'll graph what the arctan looks like. Okay, so the tangent, the standard restricted domain is negative pi over 2 to pi over 2, and so we can pass the horizontal line test, so we have an inverse function. And there is there's the tangent, just a rough sketch. Okay, now if we want to find the inverse, we're going to switch all the x's and y's, so those vertical asymptotes of negative pi over 2 and pi over 2, those are going to change into horizontal asymptotes of y equals pi over 2 and y equals negative pi over 2. So there's your horizontal asymptotes, and then we'll sketch in the inverse tangent, or the arctangent. Okay, and then we can observe, so part of what's going on here is we're going to infinity of the arctan. Okay, so as we go to infinity, looks like our graph is flattening out to pi over 2. So that's what the limit's going to be there. And so that's going to be equal to pi over 2. Now, if I wanted to find what the arctan of 1 was, I didn't remember. Well, an easy point on the regular tangent curve is the point pi over 4 comma 1, and if we're doing the inverse, we're going to switch the x and y, so that becomes 1 and pi over 4. So if we stick in 1 into the arctan, we're going to get an output of pi over 4. Okay, pi over 2 minus pi over 4 is pi over 4. Okay, and so that is going to tell us that this improper integral converges, and the integral test said that if the integral converged, then so did the infinite series. So because we got a finite number, pi over 4, that tells us that the integral converges, and thus this infinite series converges as well. So there we have our convergence of this infinite series here.